Hey everybody, welcome to another edition of Math with Mr. Douglas. Today we're looking at probability with a little bit of focus on independent events. Hopefully you have a deck of cards, some dice, maybe a spinner, and we are going to dive into probability, one of the best topics ever. Here we go. Okay everybody, we're talking about probability, and this is going to build on our general intro to probability. So I'm going to review a little bit about what it's all about, but this is a lot of fun stuff. So we're just looking at the chance of things happening. So first thing we have to do is make sure that we're writing our things and we know some key words. So again, one of the key words is going to be an event. An event, I just want you to think of is kind of like the experiment. Okay, so an event is kind of like the experiment of what you're kind of trying to do. And we basically use the letter E for that one. So that kind of makes sense, right? E. And when we start looking at probability, we say the probability of the event. So you're going to see a lot of things like this. And now we replace the E with what we're trying to do. So imagine we're trying to roll a dice. We're saying the probability of like rolling a 2 on a die. So you're putting what it is inside that bracket. And then you got to figure out, well, how do you figure it out? Well, it's pretty simple math, basically. It's just the number of ways. So the number of favorable outcomes. So the number of ways to do something, to do it. So that's the number of ways for success, right? So for success. So how many ways can you make that event be true, basically? And you're going to find different ways. Different math teachers say things different ways, but it's basically the same. And you're going to divide it by the number of possibilities. Does that make sense? So let's give you a little bit of an example to get the ideas going. And then we're going to kind of kick it up. Oh, I'm not going to be able to fit that one in there. Number of possibilities, and there you go. We're going to use the classic kind of the dice because, you know, dice, most everybody here has rolled a dice at some point in their life. And if you haven't, you should go do that right now. Stop the video, go roll a dice, right? It's lots of fun. So there's your die. And we know that, I always forget how all the sides go, but basically there's 6 sides to a dice, right? So it's 6 sides. So I just want to know, like, what's the probability of, like, just think of something. So what do you want to know what the probability of? Let's say the probability of rolling less than 3. So the probability of rolling less than 3. So how many ways could you roll less than 3 on a dice? Well, there's basically, if you had to like list it out, we'll talk about that in a second, but basically there's 2 ways, right? So there's 2 ways to do it. You can roll a 1 or a 2. And how many total possibilities were there? 6. And we always simplify. So that's just going to be 1 over 3. Now, some teachers, again, like to give you probabilities in percents. And again, it totally depends on your math teacher. I usually stick with fractions because they're a little bit cleaner. But you know, if your teacher is wanting as a percent, then you just need basically times this by 100. And you basically should be getting like 33.3 repeatings, right? Percent, boom, percent. There you go. Depends like that. Now I do want to talk about the different possibilities. Now I just said it out loud. The possibilities were 1 and 2. And we need to know some more vocabulary. So there's one vocabulary that we do need to know. So you need, if you're taking notes here, which you're being an awesome student, is sample space. So you're going to see this term always kind of come up. So sample space, I like to shorten it as SS. But basically, you're writing down like all correct solutions, like kind of all correct, or make things happen, like basically that make them true. So I say, well, just the sample space for that last one, the sample space would have been 1 and a 2. Like that. We're trying to figure things out. And what was it for, like all the different possibilities, right? So you'd have 1, 2, 3, 4, oops, 5, and 6. Okay, so just so you kind of know that if you do that sample space, I do see some textbooks sometimes talk about sample space. But that's basically what they're talking about. And the other thing we're going to talk about now is this one called the complement of an event. So the complement, and it's not somebody sitting there and clapping for you. That was funny. You should laugh. Get it? Complement, clapping. It's basically the opposite. So the complement of an event is basically the opposite of the event. So it's the opposite of the event. And for complement, because it's the opposite, we usually use a symbol with like an E and like a little dashy thing on it. I bet there's an actual word for it, but we usually use for the complement of event, we usually use some kind of like a dash like that. And what we know is that if you take the event probability and you add it to the complement of an event, we know that it always equals 1. Well, let's just go back and use that dice idea. So if you remember what that event, it was, what did we say? It was ways that we could roll less than 3. So the event was 2 out of 6, wasn't it? Well, what was the opposite of that event? So what was the complement of the event? Ways that you didn't, right? So you could have rolled a 3, 4, 5, and 6. So that would have been 4 out of 6 ways, right? So we're just saying with the event and the complement, if I added them together, so now let's put this all together. If I added them together, it would equal 1, or basically 100%. Now you might think like, so why are we all doing this? Like, okay, I get it. It makes sense. Well, sometimes it's easier to go and find a complement of an event than the event itself. And we think about that in terms of saying this. So if I wanted to find like, what's the probability? I'm not going to do it, but I want to give you an idea. What's the probability of, oh, I don't know, what's a good example of, do I want to do rolling? Sure. I'm already trying to write this. Why not? Rolling 3 4s in a row. So what's the likelihood of doing that? All right, rolling 3 4s in a row. So I'm rolling a dice and rolling it 4, 4, 4. Right? Very unlucky if you think about what 4 means in Chinese. So if you want to do the opposite of that, of not rolling, so what is that going to be? So, and you just go 1 minus the actual complement of that. So sometimes it's easier to figure out the complement of something than the actual thing itself. That's just an idea that you're going to probably get exposed to a little bit later. I just want to kind of introduce it right now. So kind of have that idea going for that. Okay, so we've got that going on. Now we want to talk about something else. We want to talk about independent events. So today we are talking about independent events. So we had our basic probability, and now we just want to do independent events and just kind of see what happens. So an independent event is basically where something doesn't impact the next thing. So where something doesn't impact the next thing. And I think we might mix it up a little bit, and let's use cards for our examples. And we're going to learn a little bit of different kind of formula for this. So I want to give you an idea of cards. So what's the probability of picking? What do dice? What do dice? Dice and cards. So of picking a king. So you have a deck of cards. So you're picking a king, comma, and that's going to be a key word, and rolling a 4. So you have two things going on. Now you have to ask yourself, are these things independent of each other? So what I mean by that is if I pick a king, does that impact what I do for rolling a dice? So think about that. I have a deck of cards, and I want to say, just color, some different colors. So I have a deck of cards, and I pick a king, and then I go and I roll a dice. Did that picking a king, did that impact the 4? Did it? Well, hopefully you're saying no right now, because it doesn't. So what do you do for these things? So what you end up doing is you do the probability of the first thing. I'm going to call this A. I'm going to call the rolling the dice B. And you multiply it by the probability of the second thing. So you're just going to multiply them. And this is also kind of known as the counting principle as well. You're going to see that. And there's different ways to do stuff. So some different things you might be hearing about this is counting principle. Not like the principle like at school. The counting principle. And you're also I'm going to show you in a second, I'm going to show you something about tree diagrams. So these are some things that kind of happen. So let's just take a look at this one. So if we had to go and actually do this question, what's the probability of picking a king? Okay, so we know that there are 4 ways to pick a king on a deck of cards, and we know that there are 52 possibilities. And we know the probability of rolling a 4, there's only one way to do that, and there are 6 total possibilities. Now, if you look at this right now, just looking at those numbers, I'm thinking this is going to be gigantic. So I multiply across the top, and then 52 times 6, what's that going to be, like 312, I think? Is that 312? I think it is. I'm going to go with that. Now, 4 out of 312. So this is where it's interesting, right? So what is that? As a percent, which I think is an important thing to do, because it kind of helps me visualize stuff. If I converted that to a percent, it's 1.28%. So that means like basically 1 out of 100 times, a little bit more than 1 out of 100 times that will happen, which is really, really low when you kind of think about it. So whenever you have 2 things that are happening, we call those independent events, where they don't impact each other, then you just go and multiply. Now you might be wondering, like, well, what happens if something does impact another thing? Well, we call that, of course, a dependent event. And we're going to talk about this in another video, but I'll just give you a little preview. So a dependent event, you kind of do the same thing, but you have to be very careful. So dependent events, the first thing that you do, it actually impacts the second thing. Does that make sense? Okay, well, because it's dependent upon it. So I'll give you an example. So what's the probability, there we go, of picking a king followed, so right after, followed by a 5. So is that going to impact it? What do you think? So is it going to impact it? Well, it is. Now, do you know how it'll impact it? Well, here we go. So the probability of picking a king is just 4 ways out of 52, right? There's 4 ways to do it, and there's 52 cards. But I've just picked a king. How many cards are now left? Oh, 51 cards. So that has an impact there. So now it's 4 out of 50 times 4 out of 51. So because I took a card and I didn't replace it, so I'm going to write down here, no replacement. And that word replacement is going to be very popular in a lot of your worksheets and textbooks. So it did have an impact, because now that first time of picking a king, it really did impact picking a 5, because now there are fewer cards to pick from. So I just want to kind of give you a little bit of a preview of that. And the last thing I want to talk about is tree diagrams. So tree diagrams are pretty cool. And T diagrams, tree diagrams kind of show you the counting principle and they show you this idea of multiplying. So how do they work? Basically, you draw each event and leave some space here. And I'm gonna have the probability, here we go, of rolling two ones. So just, hey, what do you call that when you roll two ones? We call that snake eyes. Call that snake eyes. I don't know why actually. Snake Eyes is also probably my favorite G.I. Joe character. Anyways, so rolling two ones. So here we go. Are these dependent or independent events? When I roll those two dice, does that first one influence the second one? Does it? The answer was no, it does not. So these are independent. So I'm going to go and multiply them. So if I was going to go and just do this, it would be the chances of rolling a 1 the first time. And I just multiply it. Chance of rolling a 1 again the second time. So your chances of actually getting snake eyes is 1 out of 36, which, let's be honest, is like around 3%. It's like less than 3%, I think, which is pretty low. But I want to show you the tree diagram. And this really helps. So here we go. And I'm going to start right here. And that's going to be your first event. So this is your starting point. This is where you start. So imagine you're sitting there and you have a dice in your hand and you roll it. And the first time that you roll it, what ends up happening? So you're going to show, on tree diagrams, you show all the different possibilities. So here they are. I'll draw one up there. You could have had a 1, a 2, a 3, a 4, a 5, or a 6, right? Yes? And then you roll the second one. But you wanted, so this was your first. And now what's going to happen is if you rolled a 1 the first time, what could happen the second time? Well, you could roll a 1, a 2, a 3, a 4, a 5, or a 6. So take a look at how my kind of cursor kind of goes right now. Is that I could have rolled a 2, and then I could have rolled a 4. A 2 and then a 4. Right? I could have rolled a, actually, you know what? That's not, I shouldn't have shown it that way. I was just drawing really, okay, this was just for the ones. So I could have rolled a 1 and a 4. There we go. I could have rolled a 1 and a 1, snake eyes. A 1 and a 2, a 1 and a 3, a 1 and a 5, a 1 and a 6. But you know there's also the other option, which is rolling a 2 and a 1, a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, and a 2 and a 6. I could have also gone and rolled a 3 and a 1. Do you get the idea right now? 3 and a 2. Do I need to do this all for all of them? Because I could. And it goes so on and so on. So quite quickly, I've got to run out of it, out of all the different kind of room right now, because I'm trying to do this really neat. Can I get 6 in there? I don't know. Probably not. Trying to squeeze everything in. But the idea is for tree diagrams, you actually see all the different kind of possibilities, right? So you would see all the different possibilities. Then you can just follow the tree, the branches. So these are kind of like branches, and you can see them. What I do want to highlight, though, is at the end of all of your branches are the total possibilities. Think of it as a denominator in your fractions. And you want to go and find that little solution. So that solution was right there, wasn't it? This was the 1, 1. That was the snake eyes. So there was only one way to do it. And there was 36. So that's why your total is 1 out of 36. So you can use tree diagrams to show this. The quick math way is just to go and multiply the two different possibilities. But I didn't want to show you that. I'll give you one example, then you'll all be done. Let's go into superheroes. So a superhero is dressing in the morning. So here we go. A superhero. A super is choosing her outfit. She's choosing her outfit, and she has 3 capes and 5 masks. How many different outfits could she make? How many different outfits could this superhero make? And you're assuming that these capes and these masks are, of course, different. Different fits. So I want to show you just the tree diagram really quickly. So let's say she had masks. And so here's the starting point, right? Here's your starting point. And she has 3 different capes that she could choose. Maybe she has a red one, a blue one, and a green one. And then she has 5 masks. So if she chose a red cape, she could then go and choose any of the 5 masks, couldn't she? And she could choose, if she chose a blue cape, she would still have any of those 5 different masks. And if she chose a green cape, she could choose any of the 5 masks. So if you just take a look at that, how many different, or asked you how many different ones were there, different outfits, just count all the very end of your branches. So you can see there, it's basically going to be 3 times 5. So there's going to be 15 different outfits that this superhero could go and make. If you wanted to know the chance, and let's just say for fun, let's say the masks, say there was different colors, let's just say the masks were, I don't know, let's say there was like yellow, oops. Say there was a yellow, there was a pink, there was a black, or say, I don't know, green, orange, what are the colors? Violet, sure, and I don't know, turquoise, right? If I asked you, what's the chances of her doing a red cape and a violet mask? So a red cape and a violet mask, how many ways were there? Or what's the probability of choosing that? I would say there's only one way to do that. So 1 out of 15. So just kind of realize that using the counting principle or the tree diagrams, I'll say you can go and figure that out, the probability. So a little bit, and this of course would be independent events. And then you could just go and multiply them. Pretty cool, right? So if you did the multiplying, so just, what the chances, the first one is like 1 out of 3 times 1 out of 5. Oops, that's multiplying. And that's where you get the 1 out of 15. So again, a little bit of probability, and we're getting into independent events. And yeah, hope you had some fun with that. You guys a little good idea. Until next time, do good things. Be a superhero. Thanks everybody for tuning in. All you math Padawans, great job out there learning about probability. Until next time, do good things, and see you soon.